Non ho preparato niente. Italiano o inglese?
Inglese, 2 minuti.
Che dico? Chi è che deve essere collegato? Edo Ambre, quello americano, come si chiama? Ravel?
Non c'è nessun americano.
Navel.
That's okay.
Questa è la prima reazione. Questa è la tua?
Sì.
Pensavo fosse la reazione della ragazza. Ok. Aspetta allora che te la condivido su Zoom. Zoom. We can get start, Bill. Okay. Good morning. I think that is the hour to start our meeting. Welcome in Assisi. I'm very happy to have you on live, not online, on live. It's very important for us. It's not important the numbers. In 2019 we was 150. Now we are 25, I think, 30, I don't know. But it's important to watch the face, to touch with COVID rules, naturally. And I think there's the word to Mr. Bill that can explain some rules, the program, I don't know. Welcome for all problem. Speak with Bill. No, speak with me. Welcome. Okay.
Well, thank you very much, Claudio. Over the last few days, we've been learning about Dante, so I couldn't resist the temptation to show that even scientists know a little bit about Italian literature. And Dante, in his Descent into Hell, wrote in beautiful Italian, which I've translated extremely badly into rather common English, consider your origins, or it should be your descendants, the future generations. You were not made to live like brutes, but to follow virtue and knowledge. And, you know, we all think of ourselves as heroes of the cold fusion age. And let's set our standards high to improve our science, improve the quality. And that's exactly what these workshops are for. 28 years of workshops now, starting in November 1993, when Fiat organized a truffle conference in Asti. And I took over in 1997, and we've been holding these workshops mainly in Italy, but one was held in Toulouse in France a few years ago. And of course this year we're in Assisi for the first time, though I should say, of course, ICCF 22 was held in Assisi 2 years ago, and I'm full of nostalgia and pleasure to be back here again at the Hotel Domus Pacis. As Claudio was saying, we're about 25 people, and we've only recruited European participants this year because it's very difficult to take intercontinental flights with the risk of flights being cancelled, of quarantine and other restrictions being imposed at the last minute, it's a number of intercontinental participants have needed to cancel. But I'm not worried about this. I knew there were going to be problems. I told everybody that we were going to go ahead regardless, and they could cancel without giving any reasons at all, up to 2 weeks in advance. And I think this policy has paid off. So as we're only 25, financially we're going to break even, but I expected to make a loss, and in fact it's not nearly as bad as I thought it was going to be. That's why. Workshop meals are all included. Breakfast, lunch and dinner are all going to be served downstairs now. It says meals are served in the gardens. That was the original plan, but it's getting a little bit colder and it's rained a couple of times over the last few days. So in fact, meals are going to be downstairs as usual. If you have any dietary requirements, I know there are 4 vegetarians amongst us. Make quite sure your waitress knows in advance. Be punctual because there's a lot of people to serve and food gets cold if people don't turn up. So lunch is at 1 o'clock and dinner is at 7:30. Workshop publications, there are 2 distinct things I have in mind here. First of all is the idea that your PowerPoint presentation, if it has the right name, will be put online. And my software automatically tries to see if there's the expected name, and if it finds it, it will put it online automatically. It saves an awful lot of trouble to do this, rather than do this by hand. But if you give the wrong name, you won't find it online. It's as simple as that. Secondly, you can contribute your papers to the J.C. Winners Journal, and Jean-Paul Piperian, who is the editor, will give any more information you need about that. Maybe later on, maybe at the end of the conference, you can say a few words about that, Jean-Paul. And we'd love your digital photographs too. So if you've got some nice snaps of dinners and talks and drinks and whatever, that would be much appreciated. All the presentations are 30 minutes, which is a bit longer than an ICCF, but moderators will enforce the time limits fairly strictly. My instructions to moderators would be that if a coffee break is about to come up, you can overstay by 5 or 10 minutes or something, because the coffee breaks are half an hour long. If you want to look at the program, the link is here. You can probably just get your phone out and find out what the latest changes, if any, are. I don't foresee many changes being made now. People are getting quite disciplined at sticking to the timetables, and the program has been online for a couple of weeks, and people have asked for changes from time to time, and I think this is the right way to proceed. In the past, people have taken advantage of the fact that the program is very easy to update, but I don't think that's going to happen, so you can be fairly sure that the program is correct. And I would ask you also, if you haven't already done so, to number your slides. This is very helpful when questions come up at the end of a presentation and someone might refer, can you go back to slide 13? But if the slide is not identifiable, you waste a lot of time toing and froing trying to find the right slide number. If you fancy a certificate of attendance, just ask, we'll print one out for you. Similarly, if you need an invoice for your institution, we can do that for you. Getting help, well, we're such a small community here that I think that you just have to ask anybody. Most people here have come to my workshops in the past. They know more or less how to solve problems. Getting back home after the workshop, this is the web address for the Italian train system. You may even be able to buy your ticket in advance. and you can print it out either at the printer there with us or at reception. And the website is also in English, so just click on it. On the day of your departure, make quite sure your room is free by 10 o'clock, and any personal debts, such as drinks or whatever, have been settled. So if you've got any ideas for improvements, complaints, suggestions, or whatever, do speak up. I'm always willing to listen and explain why we do things in a certain way sometimes if it may not be clear, and maybe you've got some good ideas for future meetings. Or if you don't want to speak, just email me at the website here, the email address. Thank you to our sponsors. I won't name you all. In fact, I've abused the French Society Jacques by putting your logo up here, but I'm sure that's not caused any problems, has it? I'm sure everybody knows that in most of Europe there's no smoking in any buildings, but I put it up anyway. If you want to smoke, just go outside. The COVID rules are not being very strictly enforced. In theory, we should be wearing masks inside all the time, but I don't see anyone wearing a mask here, which is perfectly acceptable, as far as I'm concerned. There are bottles of disinfectant floating around the hotel. You can use that. And the so-called green passport, which probably most of us already have, is not really required if you're a resident of the hotel. So the COVID police are not going to come around and check up, I don't think, and everything should be fine. At the end of the workshop, there'll be a little time for some discussion, and I thought I would suggest, put into your minds a germ of an idea of some things which we could discuss, but you can talk about whatever you like at the final discussion. So one thing I would suggest is, do your experimental results support any theoretical model? Because if we design experiments to test models, we're going to make progress. If we just randomly change parameters, progress might be a little bit delayed, shall we say. I don't know about most of you, but we've been working on this now for 32 years, and the progress has been a bit disappointing, to be quite frank. We don't know what the theoretical models are appropriate, and in my humble opinion, the experiments being done are not really testing those theoretical models, and the theoretical models are not making the appropriate predictions to help experimentalists. So we need a closer collaboration between these two disciplines. So the next question is, are your theoretical predictions consistent with experimental results? And typically, some of them will be and some of them won't be, but it'd be nice to discuss them, and perhaps we can find ways of improving theoretical models, refining them in some way. Just because a model makes wrong predictions doesn't mean the model is completely wrong. You can still recuperate something from it, perhaps. And perhaps later on during the theoretical speeches and presentations, we'll see some examples of how models evolve and are improved. So, continuing on this theme of the final discussion, we might want to think about what kind of experiments should we be doing and why should we do them? Is there still any point of doing calorimetry uncorrelated with nuclear measurements? This was an idea which Francesca Celani brought up yesterday. How can we identify the processes underlying the anomalies of condensed matter nuclear science? And I'm very pleased to see so many scientists from Poland, because this simulates the idea of how different groups in different countries can collaborate together. And I think this is extremely important. In unity, there is strength. You avoid waste and duplication. So let's encourage international cooperation. Well, thank you very much. That brings me to the end of the opening address. A COVID test?
For those that need to take an antigen or PCR test before they're allowed to leave the country, how do they do that?
I will find out for you.
Thank you.
Would anyone like to bring up a subject which we can think about for discussion on Wednesday? No. Okay, well, I think we must pass to Natalia. Not quite sure how I do that. Are you the last one?
I have it, but something is wrong with the camera, I think, again.
Something?
Yeah, with the camera.
Okay, don't worry.
Okay. Okay, thank you very much. Good morning, everybody. My name is Natalia Targosz-Sleczka. I represent the University of Szczecin, Poland. And I want to thank the organizers for giving me the opportunity to speak about our reactions that we study with our accelerator in Szczecin. Today I would like to focus on the future study on proton-induced reactions on lithium isotopes. So these will be our plans for the future concerning what we know so far. I would like to say today what we understand so far from the experiments that are being done with the accelerator. We do work on low energy nuclear reactions with the accelerator system for over a decade now, so we do have some experience. Although we went to astrophysical conferences, nuclear astrophysical conferences, and this was the physical society that I knew so far. So this is my first cold fusion conference, and I am very happy to be here. Yes.
If you can move
Yes.
one moment. Ok, perché però succede questa cosa? Ok. Which is your? Aspetta, qual è la sua? Questa? Which is your? This? Clean?
This one.
Ok, F5. Ok. Questa no, questa qua, ok. Ok. Oh, excuse me.
Still no camera.
Riesco un momento. Perché non funziona il video?
Okay, so in the reactions that we studied so far, there are a few important things that needs to be considered. And first is that the reactions that are taking place at low energies, they are governed by so-called penetration through the Coulomb barrier. And this this is the key point that determines the phenomena. And this penetration can change drastically due to so-called electron screening effect that I will speak about in a few minutes. The second point is that the energy excess that is produced in the experiments that you all do, it is produced in decay channels that have charged particles. Okay, so from our point of view, from the nuclear physics point of view, the experiments that are giving some radiation are not the ones that will produce the huge energy excess. Then we also have to think about the fact that Bill already mentioned, and this is the fact that the experiments are not easily reproducible. And we also think that there might be the screening effect which is responsible for this because we need to arrive at some specific conditions that we don't know so far. We need to use materials that are also good enough to reproduce the experiments that were successful so far. And the last point is also something that Bill mentioned, is that we should have a theoretical explanation of what we measure in our laboratories. So we need to have the description that will allow us to collect every important issues that are describing the phenomena that we study. Okay, now it doesn't work. So firstly, I would like to focus on nuclear reactions that are taking place below the Coulomb barrier, so for low energies of the incident particles. The most important part when we study such reactions is the tunneling effect through the barrier, which, as I told already, gives you the probability of a transition through such a barrier. So if we have two nuclei that we want to have a reaction between them, they really need to overcome the electrostatic repulsion. So they need to be brought to a very close distance between one another and overcome this electrostatic repulsion. So for that reason, the tunneling effect is very important. So you can see over here that there is an incident particle that comes to this Coulomb barrier, and it needs to be crossed or transferred for the reaction to occur. So the probability of such a transition is given over here. This is so-called penetration factor. And you see here, this is the gamma of energy, which is the factor that tells us about the height and the width of the Coulomb barrier. We see the energy of the incident particle, and this is the exponential part that is the most important to understand what is the cross-section given below of such a reaction. Okay, so the probability for such a reaction to occur at some specific conditions. In astrophysics, as I told you already, I've been going to conferences like that. In astrophysics, we use the cross-section definition in the form of this kind. And here you have the astrophysical S factor, which is another part that is taking into account all the nuclear physics effects in it. So here you have on the right-hand side top figure, you see how the cross-section is changing with the energy. So if we go for lower energies, the cross-section is decreasing very steeply. Okay? This is why we do not observe the nuclear reactions at low energies that often, as in the case of high energies. And probably this is why the high-energy nuclear physics is so popular, right? It is easy to, let's say, do the experiments there. So, but we need to also remember that there might have been some effects, if we consider specific reaction, there might be some effects that we need to actually find measuring the cross-section. Because what people usually do, this is S factor, on the other hand, also considering the changes in energy. So the S factor for a simple process with no screening, no weird stuff going on, is a simple, you see, very, very flat behavior. And what people usually do in astrophysics is that they measure for high energies and they just extrapolate. You see there is this extrapolation region. They extrapolate to low energies to know the cross sections there. But this is actually something that we do not want to do because we miss a lot of data, okay? So if something is happening there, we just miss this if we simply extrapolate. So this is why we need to actually study the low energies for nuclear reactions. Okay, and now I will briefly mention the electron screening effect. And for details on the theoretical description, I would like you to see the next talk of Konrad Czerski. So maybe the details will be explained by him. I just want to show our consideration on the proton-on-lithium reactions. So here you have almost the same scheme, but showing something, something weird over here. So this is the situation when you want to have a nuclear reaction that is taking place in a medium. Okay, so for example, if this is a metallic medium, then we have the electrons of this metal that can help to this reaction to occur. Okay, so what do I mean? I mean by that for example, if you have a reaction between two nuclei that is taking place in metallic media, then the free electrons of this metal can be collected around the reacting nuclei. Okay, so the electrons are of course negatively charged, the nucleus is positively charged, so they will attract each other. Okay, so around the reacting nucleus, we will have the electron cloud that will be formed, and this cloud will allow to lower the barrier. Okay, so you see the barrier is reduced in height and in width, and then the probability of such a reaction is higher. And how this is possible? This is possible because of the electron screening effect I mentioned before. So this is the regular electrostatic potential formula, but it has to be multiplied then by this factor which is called the screening function. If we take this, if we extract this into the Taylor series and take only the first meaningful part, we will have the screening energy of such a kind that can be defined by the screening energy function. So you see here that the screening energy is the product of two charges of the two reacting particles, and it is divided by so-called screening length. Okay, so this is the length at which the electron cloud actually helps for this reaction to be processed. So this screening energy is actually a factor that reduces, or by which the Coulomb barrier is reduced. Okay. And if we take this into account, we can rewrite the penetration factor and the cross-section using this additional factor UE, so the screening energy here and here, as the factor that reduces the Coulomb barrier. So the exponential part is changed by this additional factor. And here is the plot for, I think, gaseous targets. Okay, so this is a very, let's say, maybe not that very old, but an old paper. Okay, so this is an old paper that shows what is the effect on the S factor for this electron screening. Okay, so if this electron screening effect is occurring, then the S factor is behaving like this. So it has the true influence on the experimental data. Okay, so we can see it in the cross section, we can see it in the S factor, we see it in so-called enhancement factor. I will explain in a second. Okay, so this was about the theory of electron screening effect. Now I would like to follow with the experimental stuff, but the details again will be given by Mateusz Kaczmarski's talk, and this will be done after Konrad's talk. So experimental procedure will be explained there. What I have here is this is our, let's say, regular setup for the accelerator study. We have an ion source. From this source, we have some ions that are being produced. The ion beam is extracted and being forwarded to the target chamber, you see over here. Inside of the target chamber, we have a target, which is usually, in our case, a metallic target. So this target is firstly implanted by, for example, deuterons. Okay, so the deuterons are firstly implanted into the target. Then the ion beam of deuterons again is pushed inside, and the collision between deuterons from the ion beam and the deuterons that are already inside of the target, the collisions can happen. Okay? And the products of such collisions are then detected with charged particles detectors. And this is the scheme of my PhD thesis experimental setup. So there were 3 detectors there. We could actually find angular distribution of the products that were produced within the target. Okay, so this is the sample spectra of such a study. Okay, so for here I have the data for DD reactions in zircon. Oh, sorry, this is tantalum, yeah. So in a metallic target. Okay, and we clearly see what are the products. Okay, so this is helium-3, triton, and proton. 3 lines clearly visible, and we can actually say how many of them were produced. And from this, knowing additionally the density of the deuterons in the target, knowing additionally what was the current at the target, we can extract so-called enhancement factor. So this enhancement factor is showing the points. These are experimental points. And for such a plot, we use a single fit line to find the screening energy, which is here of the value of 297 electron volts. What I want to mention very briefly is that it is easy to, sorry, there is no data on the energies here. I don't know how it happened. Maybe, okay, I don't know. So probably this is between 10 and 20 or something like this, kilo electron volts, and the screening energy is in electron volts, okay? So what I wanted to mention is that it is quite easy to measure the high energy points because it takes not that much time. It is quite easy to do that. But if we go for lower energies, the statistics is very, very poor. So we need to wait for hours, days, or even weeks to actually have enough data for the specific energy at low energy range. And as you see also the error bars there, are usually higher because when we measure for a long time, we get oxidations and we get some impurities at the target surface. And then we are not that very sure about the energy at which actually the reaction was occurring. Okay, so then the error bars are also bigger at that point. Okay. So here are the results using this technique that I showed and other techniques. Many people around the world studied the electron screening effect. These are the data collected until 2008. So there are a lot of data, including metals, insulators, alloys of different kind, gases, and stuff like that. And for example, what I want to show here is that if we take into account zirconium, which is the charge of 40, there are different values of screening energies, as you see. So the differences between different techniques of experiments and different analysis methods are really doing, very, very much difference. So this is, it is hard to compare between different authors sometimes, and we really have to take very different stuff into account to actually understand what happened and why the discrepancies are so big. And here you see another experimental collection of data. And here I want to show that this is something weird that we still don't understand at the moment. And for example, okay, so this is the, let's say, amount of deuterium inside of the metallic target. We have a whole bunch of different points for very, very low screening energy value. Okay, so the amount of deuterium could be very, very small or very, very high, and still the electron screening energy was not that much. And here we have another group of points that is also very weird because you see that for actually almost nothing implanted, we can have screening energies that are ranging very, very drastically. So this is something that we don't understand. We have some other points from our experiments that go maybe more along this direction and change this plot at some point. But they are not put here because this is the original plot taken from the paper here. Okay, and now also Bill mentioned that we need to understand the experimental data in terms of the theory that describes it, and do they actually agree or not? We have to think of this also. So this is the two plots here at the bottom are showing the experimental data from high vacuum experiments. So these were, let's say, old experiments. In blue, you see over here. And we have this theoretical description that is shown in red. Okay, for theory, we will able to calculate the electron screening for many, many different metals. Here the experimental values are only a few. So you see that the experimental values are in discrepancy with the theoretical prediction, right? And this is what we think. This is because of the high vacuum conditions that were not that pure. Okay, so for our experiments, it is very, very important to have the very clean target. And if there is some carbon, for example, inside of the target chamber, or oxides or whatever else, it just diminishes the effect. Okay, so these are high vacuum experimental results, and for the ultra high vacuum experiments, we do not have that much data, but we have some data on zirconium. And we suppose that this experimental data will be, let's say, pulled down to the theoretical values. Okay, so if we will have the pure system to actually study this in details, we would be able to take that down to the theoretical values. Okay, and here maybe I will mention here also, you see that there is this structure again in theory and in experiments, and the structure comes from the fact that inside of a metal, not only the free electrons can contribute to the electron screening effect, but also the bound electrons are polarized, and they help a lot. And this is what is taken into account in this calculation. I mean, here in red. Okay, and now I would like to mention our predictions for the nuclear reaction rates. Reaction rate is a product of the nuclear cross-section, the relative velocity between the two reacting particles, and n is the density of the specific nucleus inside of this material. So we have to take into account that this cross-section is the cross-section for a screened reaction, and if we go to low energies, so energies going to 0, this expression for reaction rate will be simplified in that form. And what I want to say is that this is something that was calculated also a few years ago by Conrad, and he published this in 2004. With our experimental data, which are shown here in this yellowish, let's say, band. If we have screening energies of the values between 200 and 400 electron volts, we can, okay, so this curve was calculated, sorry, I have to mention that, for DD reactions inside of palladium target, okay? So this blue curve is for such a reaction. And if we would have the screening energies of the values between 200 and 400 electron volts, we are reaching the points that are shown here. These are the data made by Jones, and he was measuring neutrons in nuclear reactions. We have here Fleischmann and Pons excess heat measurements, and we have here the theory of Kunin that disagreed that cold fusion is possible. And what I want to say is that we can explain what Jones actually published. We are still a few orders of magnitude far from Fleischmann and Pons, but if we would have higher energies, screening energies, we would be able to reach that point, okay? So if we will find a specific material and the specific conditions that we will understand, then maybe it is possible to actually reach the region that was shown there. And I wanted also to explain why we think that Kunin was wrong, disagreeing with cold fusion, and this is because he actually theoretically calculated the energies for deuteron molecules. And we know that the nucleus behavior is very, very different from the molecular one. So we think that this, the conclusions of Kunin are not really valid at this point. Okay, and here are the calculations for comparison between deuteron-deuteron reaction and proton on lithium 6 and proton on lithium 7. So in blue you see, okay, so this is cross-section and this is the reaction rate. The calculations were made for this specific values of reactions. Mu here is the reduced mass for the entrance channel, S is the astrophysical S factor, and Eg is the gamma of energy. And for these data, we've calculated the two things here. So the cross-section, you can see, is the highest for DD reaction. And then we have the cross-section of P on lithium-6 and P on lithium-7. These are given for screening energies. Of the value of 100 electron volts for DD reaction, and because the charge of lithium is 3 and the charge of deuteron is 1, we suppose that the screening energy might be also 3 times higher in case of the reactions with lithium than in case of deuterium reactions. So these are the cross-sections, and here are the reaction rates. So you see in blue, once again, this is the reaction for deuterium on deuterium, and then we have proton on lithium-6 and proton on lithium-7, and these are reaction rates versus the screening energy values. Okay, so if we have the screening energy of a value of 400 electron volts, so this is the value that we observed many times in our experiments, then we can see that the highest reaction rate is for deuterium, okay, DD reaction. But, for example, if this value is 3 times bigger, right, because of the lithium participation in this reaction, so if we go from 0.4 to 1.2, so 1,200 electron volts of electron screening energy, then the highest reaction rate is actually for the proton on lithium-6 reaction. Okay, so we think that these reactions are very, very important from this point of view. That the study should be very interesting. And that's why we actually want to study them experimentally. Okay, and here I just want to briefly show how the cross-section can be changed due to the changes in the screening energy value. So once again, in blue you have deuterons, in red and orange you have proton on lithium-6, and in green you have proton on lithium-7. So the lower curve for DD reaction is for 100 EV screening energy, and the higher one is 5 times that, okay, so 500. You can see by that many orders of magnitude, the cross-section actually changes, okay? So the probability of such a reaction goes up very, very crucial. But then in the case of lithium-6, which is the reddish curve, are the reddish curves, you see also a jump which is even higher, okay? But this is, again, 5 times the value, so 0.3 up to 1.5. And again, the same situation for the green lines on lithium-7, okay? So the changes are really very, very important. Okay, and the last point before my conclusions is something that is only, let's say, very, very preliminary. And this is the usual formula for the cross-section that I showed already, okay? So this is for the cross-section that takes into account the screening effect. So we have the screening energy included here and here. And this exponential part is the most important, okay? So it governs the whole phenomena. EG here is explained in details. Once again, mu is the reduced mass. Okay, so we have the charges. The charges here come in the square. And if we go with energies to 0, again, so we will consider the low energy nuclear reaction, this exponential part can be simplified to this factor, okay? So the E from here is missing. If we assume from our theory, it is assumed like that. If we assume that the screening energy is proportional to the product of the two charges of reacting nuclei, it implies that this part here would be proportional to the square root of the product of Z1 and Z2, okay? This would mean that the lower the charges are of the reacting nuclei, the better is the cross-section, okay? So the probability of such a reaction is the best. So deuterons actually would be the ones that should be studied more and more in this case. But if our theory is somewhere wrong, and we can assume that screening energy is proportional to Z1 and Z2 to the square, this would imply that the factor is independent on the product of Z1 and Z2. Okay, so the charges do not matter at all, and this would mean that the same probability would be reached for all nuclear reactions. So it would not matter what we study exactly. Okay, so this is something that we should think of also in the future. Okay, and I would like to briefly conclude what I said so far. I have one more slide at the end, so for the dessert. So this is what I wanted to say so far. Proton-induced reactions on lithium are very, very interesting from our point of view. We studied DD reactions for many years. We want a change, and this is probably something that will be important to be studied. The proton and lithium-6 and proton and lithium-7 reactions produce only charged particles, so the Q value of the whole reaction is absorbed in the sample, so no radioactive products, and this would be a very good candidate for having the huge energy excess. We know the channels of those reactions. We know exactly what to look for, okay? So we know the products. So this should be easy to be performed, okay? We'll see, but we suppose that this is not that difficult. As I said already, because the charge of lithium is 3 times as much as the deuterium charge, we expect that the screening energy for P on lithium-6 and P on lithium-7 in metallic media will be 3 times as big as for DD reactions. And because nuclear reactions in natural lithium isotopes are so interesting, we plan to study them in our lab in the nearest future. When this will be, we don't know exactly because we are dealing with some experimental issues at the moment, but these are the plans for the future. And the dessert, okay? So the previous studies of João Cruz, whom I also met at astrophysical conferences, and from Jiro Takasagi over here, João Cruz actually reported exactly what we want to measure at our lab. So these were, you see, proton on lithium-7 and proton on lithium-6 reactions in different metallic and not only metallic environments. And yes, for such an alloy, they went to the value of 184 in lithium-7 and 320 in lithium-6. But the most important here and the biggest value they reached for palladium-lithium alloy but the lithium part is very small, 1% only, okay? So these are the values, 3,790 EV for lithium-7 and 3,760 EV for lithium-6. And these numbers are huge, okay? We think we know about the mistakes that were done collecting the data, so we think that these values are probably too high, that there should be, the error bars, for example, should be higher, and then this is not so easy to say what was the exact screening energy value. And of course, yeah, there are some things that need to be checked. So you see here 1, 2, 3, 4, 5 points, and only 2 of them are actually laying on that curve, okay? And 3 of them are not there. So there are some issues. Of course, experimental study is very difficult, right? And the analysis there have also very, very huge meaning. And there might be mistakes, of course. But so we think that these values are too high, but this is very, very interesting either way. And this is Girotas Kasagi's results, and this was deuterium DD reactions on lithium-6 and on lithium-7, okay? So he also had palladium and gold that was studied, and the values are shown over here, 1,500 EV and 60 for gold, okay? So these are the values that are interesting and that we would like to study in more details to find out whether actually the screening energy can be that high. Okay, thank you very much. I'm ready for questions.
I liked your calculation of nuclear reaction rates, and of course the reduced mass, there's dependency, an exponential dependency on the reduced mass. So this suggests that if we could reduce the reduced mass below 1, for example with the PD reaction, we should get a vastly enhanced rate of reaction.
Yes.
And consequently, this predicts that helium-3, even in the presence of so-called pure deuterium, because of the protium contaminant, should produce enormous quantities of helium-3. And I plugged in the figures actually into the Kunin paper you just referenced, which I like actually. We'll discuss it in another moment. And there's about a 14 orders of magnitude enhancement of the PD reaction. Okay. That will dwarf any helium-4. So if we're getting helium-4, it's very unlikely to be coming from a DD reaction, because otherwise we'd see helium-3. So we're not getting helium-3 either in large quantities. So this indicates, in my opinion, that the explanation for cold fusion is not fusion at all.
Okay.
Okay, thank you very much. In a private communication with Stan Pons, he told me they've done experiments, electrolysis experiments, using LiOD, but with lithium-6 only. And they got a lot of helium-4 produced. So I think you should look at the lithium-6 and deuterium, not only proton, but also deuterium. Okay. Because then you produce 2 alpha particles.
Yeah, we need to start from something, yeah.
Yeah, I know, but I'm telling you there's some experimental facts that should be looked at, you know. Okay. A lot of helium has been produced that way. Thank you.
Thank you. Okay, thank you very much.
ECO, this
DD theory.
ECO, ECO.
Okay, so the name is DD theory. I have. Okay. This one.
Which is no, non è questo. Questa? It's this?
But it's not full screen. It's not full screen. You see here, this should be full screen.
Okay.
Okay, it's full screen now.
Okay.
I should come back to the first page. The second. Oh, the first one. Okay, thank you.
You can put a no.
Yeah, it's no problem.
Yes, you can write this because
This is the pointer.
yes, stay with that.
Okay,
Okay.
thank you.
But the phone for Zoom is this.
Okay,
If you
I will try to speak louder.
sit down, use this also with the.
Okay, this may be better solution. Yeah. Okay, thank you very much, and good morning to all audience. So, yeah, maybe closer. You can hear me. Okay, so no problem. So we can continue with some theoretical predictions, calculations, but they are very strongly connected to the experiment. And we can ask us why the theory is so important. There are mainly 3 points which are most important. Of course, if you want to understand what is going on during the experiment, you should think about theory. Okay? Theory, it means we deliver information or explanation of the experiment. This is most important point. But there are 2 additional points which are also important. If you want to measure something new, you need a kind of hypothesis theory to do something new, to check to the theory. Okay? Even the theory is not correct, it helps you to do something new. And the third point, it is also very important because if you want to convince other people that your experiments and your results are nice and give something new, you need for that theory. So if you have a nice theory, which cannot be, maybe it's not really final solution for the problems, but it is consistent and logic, it is something what we can work with, okay? So here I would like to show you that DD reactions, there's something what can be real at room temperature, and the cold fusion, it is real effect, not something, not our imagination, okay? So there is a very simple theory that is applied in different fields of the nuclear physics. So there are no extra fields, new particles. There are all the effects I will study here are known in nuclear physics. There are very nice examples, and finally, maybe in the conclusion, I can say something about it in more detail. Okay, we will study DD reactions, and usually in accelerator experiments at high energies, even you have heard here of Natalia, there are two main channels, neutron and proton channels, which were measured to very low energies. The minimum energy of accelerator experiments were 2 keV in lab. So it means it is almost 1 keV in the center mass of system. Okay, it is very close to the room temperatures, let's say 25 millielectronvolts. And for nuclear physics, this extrapolation of 1 keV, it is in principle nothing, because all the resonances known which can enhance the rates or cross sections, they are usually very broad. The width of the resonances are maybe 1 megaelectronvolts, maybe several kiloelectronvolts. And therefore, the people, you know, nuclear physicists were very skeptic about cold fusion from the beginning. And Kunin, one of the best nuclear physicists, he was responsible for rejection of the large projects in the 90s in the United States because of this missing of 40 orders of magnitude. Yeah, what Natalia already explained. And therefore, we need to know something about nuclear physics and explanation, possible explanation of the effects. So the first one, we should recognize the problems that the people have to, if you want to say the cold fusion is something reliable, something that can be observed. The first one is this 40 orders of magnitude that was calculated by Kunin in 1991 and published in Nature. Okay? And he was president of the committee discussing this large Department of Energy project applied for cold fusion. And the mistake was that he calculated screening energy and screening effect for molecule. And within the molecule, hydrogen molecule, you have bound electrons, only bound electrons. And in metallic targets surrounding host metals, there are free electrons, and they can move much faster, and they can create some collective states, and so and so. Okay, so there are many things that wasn't involved in the first studies there. There is the first point. The another point, which was very strange for the people, that most of the studies were connected or presented results that the usual channels, neutron and proton channels of the DD reactions are not so strong. The main channel should be helium-4 production, connected to the heat excess production. It is, there are some very nice works showing this correlation between heat production and helium-4 amount, just in calorimetric studies, and the parameter combining both effects, it is just very close to the binding energy of the deuteron in helium-4. This is 24 MeV. So this connection heat production and DD reaction, it is just binding energy of the deuteron in helium-4, this just 24 MeV. Okay? So for one reaction DD, we should have 24 MeV that we can use for our energy production. And the third one that we should explain if we want to say that our theory is something really good, it is poor reproducibility. Why we cannot reproduce our experiments using almost the same parameters, and we observe, for instance, a lot of spikes locally spots, local small spots of the targets where the energy can be produced. Okay. Oh. There are some ghosts here, ghost states. You know, there is a very nice situation in nuclear physics. There are some ghost states. Okay, so they are already away, so we can continue. And once again, the screening fact that is known for already 50 years and introduced already in 50s last centuries, and for the plasma physics, and this is just essential for understanding nuclear reactions in stellar interior, okay, in astrophysical plasmas. We have different plasmas, of course, weak coupled, strongly coupled plasmas, and this understood very well. But we start to study this this screening effect that just in 90s, because of cold fusion information that, and the idea was we can use DD reaction studied in metals also for astrophysics, yeah, and then after that we have measured very high screening energies far away from our theoretical predictions. It was also very important for astrophysics because the people say, okay, if the effect is so strong and much stronger than the predictions, we should correct our astrophysical models. For instance, if you speak about giant planets, they produce some energy, and what we know that the energy emitted is twice as high as predicted. And the question was, what is the reason for that? Or there is white dwarfs or supernova explosion, maybe there's much better example for that. This is just a method to calculate the distance of supernovas, and then we can recognize what is the history of the universe, of the expansion. And so if you have different screening, then the distances can be completely different, you know, because the screening can increase the reaction rates by many orders of magnitude. This is already known in astrophysics as well, okay? So, for instance, for the sun, we have the temperature 15 million degrees inside, interior, and the importance of the screening is not so high because of so large and it is not so dense plasma, so it is the problem. This contribution because of screening is only 10%, so it is not important for our sun, but for red or brown dwarfs or giant planets can be very important, or for white dwarfs as well. Okay, so it is something what have very large consequences. Once again, you see here Rutherford form of the potential and the penetration factor, just with the gamma of energy, okay? So it is just then, and if you have screening in metallic media or different other medias, we have electrons that can connect, can be collected between reacting nuclei. And here you see this explanation of the screening energy as a first term of the Taylor series. And once again, and we can include the screening energy, screening effect, just increasing our energy by the screening energy in the expression for the penetration factor. This is not really kinetic energy what we increase, just a mathematical formalism to include lowering of the Coulomb barrier. So we can do it in such a way that we increase the energy by the screening energy, but only in the expression for the penetration factor. Okay, and there are our first experiments performed already in 90s, and we are world master in going towards the lower energies. And what we measured, you see here our energy spectra for detectors. And what is important that these reactions, dp, dn reactions, are not isotropic. There is angular distribution that includes so-called p-wave contribution that makes this anisotropy in angular distribution, and therefore you have so-called A2 coefficient. This is something that gives you cosine square contribution to the angular distribution. So we know that, we can explain that. This is just results of the internal structure of the helium-4. Helium-4 in this case is so-called compound nucleus, composed of 2 deuterons, okay? We will speak about it more detailed, but it is what is important already here that the angular distribution is not isotropic, okay? And we could measure this very nice anisotropic coefficient, A2, to the lowest energies, and it agrees, for instance, with the gas target measurements as well. Okay, both metallic and gaseous experiments deliver similar results for this case, of course. And some very old experimental results measured for different metals, aluminium, zirconium, and tantalum, and in all cases this enhancement factor, this so comparison between measured rate to the, or cross section to the expected theoretically, because we know very precisely what we should get theoretically, and this difference or ratio is just screening effect, okay? And it's just this exponential-like increase of this curve. In the case of no screening, we should have a constant line equal to 1 for all energies, okay? So this increasing, exponential line increasing due to screening energy we can observe and fit using only one parameter, screening energy UE. And you see here once again the reactions, different first measurements, but there are so many measurements till since that time, you know, Natalia already shown you. And for comparison, the screening energy for gas target, deuterium gas target, is 25 electron volt compared to almost 300 electron volt metals. So you see the difference. And there was very, very huge interest about it in astrophysics because of so large difference there. And the question was, it is just metallic effect or plasma effect, because we can treat deuterons within the metals as an example for plasma as well. We have electrons, which are also plasma in metals, okay? Okay, the theory comparison you have seen already, but it is what is important here that in this theory we have included not only free electrons, but also bound electrons that could be polarized. And third effect is that the 2 deuterons placed in the lattice combined to helium-4 have different cohesion energy, so-called cohesion energy, binding energy of the atom within the lattice. So this difference contributes as well to the total screening energy. So all the effects we have included, and our theoretical values are twice as large compared to the previous predictions, but still a factor of 3 of the experimental values measured at high vacuum conditions. Okay, it has some consequences, of course, and here this presentation is much better because the parameter here, Rs, is just the electron distance in different metals. And then you see this characteristic structure, theoretical curve, and experimental. So we can be sure that our theory gives very nice metallic dependence, yeah, for different Z values. but the problem was the absolute value of that. The difference was a factor of 3 between theory. Theory gives values of about 100 electron volts, and experimental values for heavy metals was 300 electron volts. For light, for lithium, for aluminium, you see the values are smaller, of course. Only for heavy metals are much larger. And therefore, we went to ultra-high vacuum, because the problems of different measurements in the past by different groups, and this differences that was said by Natalia, is coming from impurities on the target surface. Yeah? You could see that, for this small, there is one of the purity of the target contamination of the target surface was one point. The another point was that if you have not so high deuteron density in the target, they can move during the implantation, during the measurements, and then you see something what is increased, but it's not real increasing because of screening, this is because of increase of the deuteron densities. So therefore you should be very careful, and the solution is to measure, to perform the measurements at the highest possible stoichiometric ratio between deuterons and metals, metallic atoms. And therefore you can be sure that, that there are no more deuterons at the surface, and that what you measured is really effect. Okay, this was errors that the people made before in so 15 years ago maybe, or something like this. And this our ultra-high vacuum, and about it you can hear Mateusz will say something about more. Okay, and the new measurements we have performed in using ultra-high vacuum system. It is made on zirconium, and you see here maybe you can see here that the experimental points are now have a smaller error bars, and there are no systematic or very small systematic errors, but the blue curve describing only screening, it is not nice description of the experimental results, because the curve lies above the experimental values for higher energies, and for lower energies is below, systematically. So it means there is another effect that should be contributed or involved. And this very precise measurement. So if you compare it to the previous measurements, maybe I can come back here to the old measurements, and you see there are some jumps and systematic errors, you know, and the number of the points was not so high, and therefore one parameter that we could fit here was enough, yeah. But now the situation is completely different. You see here this, we need something more. And the solution is, we thought about it already a long time before, because this usual situation in the nuclear physics. If something is missing, it means there is resonance. A resonance is a special level in the compound nucleus, and this is just the method to recognize the structure of the compound nucleus. This is just spectroscopic method to do it. And we see here, if we put a resonance in the form of Lorentz-shaped resonance, you know, and we calculate the cross-section coming from the so-called flat contribution of the broad resonances which are already known in the helium-4 because the structure is very well known. And we put additional resonance, this what we want to have here, and we do it with the coherent system. So there is a phase important because it is interference between two components of direction cross-section now, this flat and the resonance, and this phase here, cosine of this phase depends the interference between both contributions. And then this cross-section on enhancement factors should have a kind of pocket. So we will have flat course of the enhancement factor for high energies and the very strong increase at low energies. Okay, this is what if we put this contribution for the special matrix elements, because the theoretical cross-section for d direction can be described by 16 matrix elements, so-called transition matrix elements, which are known. And we put additional one for one resonance which is not known. This is our hypothesis. Then we can get very nice description of this experiment. Yeah? So we need something what flatten this course at high energies and increase the screening at low energies. Okay, this is not all. There's only one point in this puzzle. Next point is even much more interesting. We put the same contribution to the data that were measured already almost 30 years ago. Yeah, this measured by Greifer and this very nice group of Klaus Rolfs in Bochum. They measured many very nice reactions and they measured the direction on gaseous target. So it is not metallic. If this only metallic effect, this additional increase I have said we shouldn't observe any effect here. But we see the same structure if we put only screening this red curve that is above the points, yeah, and at below the high energy points. So we have, if you want to have the blue curve, then you should add this resonance. So you have not only metallic targets, but also gaseous targets. You have only single nucleus in the gaseous target. So this is not metallic effect, okay? And the contribution we can describe by because we measured DP reaction, so the partial width of the resonance, it could be an additional parameter. So we have screening energy 20 electron volts, which is for gaseous target, and the partial resonance width is 10 millielectron volts, which is very similar to that we measured or determined for zirconium. It was 20 millielectron volts. But what we measure here, or we can fit here, is just additional effect that should be included as well. We should include Doppler broadening effect because it was measured at a certain temperature. So our temperature is 25 millielectron volts. So real width of this resonance is below 1 millielectron volts. And the broadening in gaseous target is weaker than in metallic. And you see here this trend, this dependence as well. So it is really something we do nothing. Yeah, we see only our results, and you have an additional point, additional argument for this theory. And coming back to the angular distribution, here this anisotropy coefficient, this ratio A2 to A0, And for metals such tantalum and so, you have very flat cause of the dependence. But in the case of strontium target, we observe additional, these red points, additional maximum of it means the neutrons are more anisotropic than protons, and in the neutron channel and the proton channel we observe here very flat contribution, and there is no difference for tantalum and strontium, but the strontium red points once again show that this branching ratio between neutron and protons are decreasing very strongly. For tantalum and gaseous targets, this is almost constant. But for strontium, we see this very strong suppression of the neutron channel. This is something what was observed in cold fusion experiments, that the neutron channel was weaker compared to the proton channel. Both were much weaker by a factor of 10 to 7 compared to alpha production. But yeah, it is something what is also important, because we want to have an energy source that is not radioactive, and neutron production is counterproductive in this case. Okay, so we don't want any neutrons. Therefore, lithium reaction on lithium, it is so nice, because we have only known charged particles, helium-3, helium-4. Yeah, it is something very nice. And the whole energy produced can be absorbed within the target. Here, if you produce neutrons or gammas, they are going away, and then they bring the whole energy away from the sample. So lithium is something very nice, okay? But coming back to deuteron-deuteron, you see here that we can, with this resonance, explain even this branching ratio. And not only branching ratio, but also anisotropy, okay? And now the situation in the compound nucleus is very important if you want to see it. So this known states in helium-4, there are very broad states. First excited state is 0+, ground state is also 0+, and all known states here are predominantly of the structure 3 nucleons plus 1. So triton plus proton, or helium-3 plus neutron. So this is just the wave function that can describe the structures of them. Okay, so all the known levels have this internal structure. Besides, or the exception is there are this group of states here in this blue frame, which have different structure, deuteron plus deuteron. And nobody can explain why this resonances, these states, have this very pure deuteron plus deuteron structure. Yeah? There is no mixing between different structures between deuteron-deuteron and 3+1 structure. So we are speaking about so-called weak coupling between two different structures, different channels. And this was problem, why there's no mixing. Yeah? And the question is why, yeah, we can see it maybe later. And the explanation for that is something like here. So instead of one Coulomb barrier between two deuterons, you see there are two deuterons coming from outside, and they should synthesize to one helium-4 nucleus. They should go through channeling through the Coulomb barrier. But if we assume that this barrier have two minima, one for helium-4 and this 1+3 cluster structure, and another one for at larger distances for DD structure, you know, we have one helium-4, but for at larger distances we should have here some resonances of this structure, and then if you want to mix this structure DD with 1 plus 3 clusters, it should go through this barrier. And this is why it is not so easy. You have once again penetration factors that make it difficult, and therefore this mixing is so weak. It is something what is known in nuclear physics. For instance, for isomeric states, they have different shapes, and then coming from one shape to another shape is very difficult. This is a very analogous situation. We know that that the DD structure should have large radii compared to triton plus proton because of the different theoretical models. We know already this. Okay, so I suppose we have here this double Coulomb barrier, and then we can explain very well the situation. And you see here there are once again this the group of DD structure, and then here's this resonance, 0+ resonance that should be involved if you want to explain what is the origin of these states. So if we have these states here above, and they are already known, we should have also this 0+, very close to the reaction threshold, to the binding energy 24 MeV. Okay, so this very nice situation. And then the next question: how can decay this resonance? There are many different open channels. There are proton channel, neutron channel, which are already known. But if you produce this high excited helium-4 particle at excitation energy of 24, it should decay. And neutron-proton is one of possibility, but the width of this partial width of this decay probability is only 1 millielectronvolt of this very, very low width. It means the probability is very low. But we have calculated that another system, another channel should be much stronger. This internal pair production, that this excited state decay instead of gamma emission, because transition 0+ to 0+ is forbidden. It's not allowed because photons have a spin of 1, and therefore this transition is not allowed. Instead of that, we have emission of electron-positron pair, and then it takes the whole energy, but the sharing of the total energy between the electron-positron is not unique. You have the continuous energy spectrum. It is very difficult to measure experimentally this channel, because you need to measure both electrons and positrons in the coincidence measurements, and then you can sum the total energy, and then you have 23 electronvolts, because you have rest mass of both electrons here. Okay. And then we have calculated that the width in the channel is very large. It is factor 100 larger compared to neutron-proton. So the dominated channel is this one, not proton or neutron. Yeah, it is explanation of our observation. And another scheme, this internal electron conversion, where the whole excitation energy will be given to the electron sitting in the K shell of atom. Okay, there is also radio without emission and photons. You have the electrons takes the whole energy. Or the third one, in the case when the DD or deuteron density is very large in the metals, we can speak about hydrogen molecules within the metals. And we have two deuterons which are placed very close to each other, and then the third deuteron coming to that collide with one of them, and then produce this excited excited state, and then decay, it is just transferred, the whole energy will be transferred to the deuteron and this ground state helium particles. So we should observe deuterons of 16 mega electron volts and alpha particles of 8 electron volts. But the probability for this mechanism, for this channel, is I haven't calculated them now, so it is a question mark still here. But it can be very important if the density, deuteron density, is very high. So this is just a future issue for theoretical calculations, but I know already how to do it. Okay, and the final piece to the puzzle is that, you know, the value of the screening energy that the people measured before and we measured now, our last measurements of screening energy in zirconium deliver 100 electron volts, very close to the theoretical prediction made already, let's say, 15 years before. So, okay, and now our experimental values made in ultra-high vacuum are very close to that we have predicted 15 years ago. There are no problem. But how we can explain this difference, 100, 400 electrons the people measured before? And this is the solution. We have started the measurement for one energy. It was 15 keV of deuterons, and measured the screening energy at different time after cleaning the target. So the first point was made with the clean target. We used argon ions to clean the surface, and then waited a little bit and measured the screening at different, after 2, 4, 8, and 24 hours after cleaning the target. And what we observed, that at the beginning, we could measure that very small contamination of the target by the carbon or oxygen caused an increase of the screening. So this original point we have used for this first figure I have shown you, yeah, we measured always with the clean target. But if we have a small contamination, the screening was increased. And this change from this point to this point after 3 or 4 hours corresponds to change the screening energy from the 100 to 400. So if you measure it with almost clean target, but not completely clean, almost clean, that you have then this large screening energy. So it means that contribution coming, very small contribution, yeah, this, it is maybe 1 atom per 1,000 clean atoms of the metallic can change the screen, okay? So it is something what is, we say, okay, this small contribution from the oxygen or carbon can change the lattices, can localize electrons locally. And it leads to the increase of the so-called effective mass of the electrons inside of metals. Usually, electrons in metals have the mass equal to the free electrons. In some metals, for instance, nickel is one of the metals that even in the pure system you have 20 times higher mass compared to the free electron, 20 times higher, okay? But usually it is equal to 1. And if you have small contribution from the, let's say, localized orbits of electrons, you have then completely different screening mass, and then the screening energy is proportional to the square root of this mass. So this explanation of our experiments, I'm going to the conclusion. To the conclusion of this last picture. And then you see here the prediction extrapolation to the rim temperature for the cross section. You see here this resonance at different place because we cannot say where is this resonance precisely, at what resonance energy, but this, the width is 100 milli-electronvolts, and you see what is the dependence of the cross-section and corresponding rates between different screening energies. There's 20 orders of magnitude at room temperature, and this very nice situation. So we can explain why the cross-experimental values are not so easily reproducible. Yeah. So this, and the question, and then this resonance can be shifted locally depending on the impurities locally. So this is a crazy situation. And then you see at the top of the resonance, the reaction rates, and so it's much higher, 7 orders of magnitude higher than of the resonance. Okay. This point you see here, you have seen already, and then the conclusions now. Very quickly. So once more. So we see that electron screening can be here in the range 100 to 500 electronvolts. This huge difference at room temperature. We need 0+ threshold resonance in helium-4, yeah, to explain the branching ratios. And then we have the real helium-4 alpha particles as a main particle produced in the cold fusion. And resonance decay say us that what we can measure in the future or should look for, this electron measurement, they haven't been measured till now, okay? And another possibility is maybe to measure alpha particles and deuterons at 16 and 8 MeV. Okay, thank you.
We have no time to question because the coffee break is at 11, but it's 17 minutes later. Please. And I ask the people, when we are in the hotel, we must use the mask, not during the coffee break, obvious, but in Italy it's needed to use the mask in the hotel. I'm sorry, but I asked the people ask me why you don't use, okay? Please, the coffee break is here, near the door. Thanks. A quarter for the coffee break, okay? Thanks. It's don't.
This might, yeah.